Yeah. I see that we're now live on YouTube. See that? Very good. So we're waiting a couple of more minutes for people to connect. It's not even 11 a.m. East time. Okay. Okay, there's a query. Oh, why? So I do not have access to the Q&A. I see that somebody asks something, but if I click on the button, I don't have access to it. Don't know if it's normal or not. Hello. Yeah.
Yeah, I'm looking at it. You should have access to it. I'm not sure why you wouldn't. Let me look around and see if I can figure it out.
Yeah.
The question is, will Raul Brasenio join us today?
Oh, I don't know about that.
I don't think he's here this week.
Yeah, so yeah, maybe not. It's fine. I can just introduce myself. But if no, I see it. Sorry, I have two screens, and it's just that I was clicking on it. It was popping up on my other screen. Okay, I do see.
Yeah, and I just cleared that question. Sorry. So, but
okay.
yeah, you'll see it when it pops up again.
Yeah. Now I understand it. It just popped on my other screen. All right. So I'm guessing the sound is okay. Can you? I don't have to.
Yeah, sound is lovely. Everything looks good.
Okay. So maybe and I see that we have like several participants already, probably more live on YouTube, and then it will be available on at a later date on YouTube for people who join us in a different time zone. So maybe I introduce myself. I'm Vincent Mathieu, professor in Barcelona University, a colleague of Raul and the other people who will participate to this program. So this is the REYES program. So this part of the REYES program is organized around webinar on introduction of nuclear physics, kindly organized by the staff people at Berkeley University. And there will be different parts. So I will talk today and next Friday, same time, same link on the same topic. So there will be other part given by other colleagues, Andrew Jakura, Wyatt Smith, Dimitra, and others. So in this first part, I will talk about kind of some introduction to nuclear physics from an historical perspective. Now, the historical perspective is kind of an excuse also to introduce some physics concept along the way. I found this perspective to be interesting also because it's typically not taught at university. I mean, the reason, of course, is that it's, well, typically the teacher like me, that we are not historian, right? So there's a disclaimer. I will talk about historical facts, but I'm not myself an historian. It's just information I could gather on some different resources, mainly internet. But one of the reasons also is that before, typically when we taught some, let's say, nuclear physics or a particular topic at university, and we wait that the subject has been mature enough and to present the idea in a coherent way. Typically, if we go back to some historical development, the ideas at the very beginning are not mature enough by definition. So people are still working on some concept, and it's only later on, maybe a decade or two later, that people have understood that properly and can present it, teach in a more coherent way. So that's typically a difficulty when we present an historical perspective, is that all the ideas that we introduce might not be presented in the current way, but as they appear, right? So here in this talk, I will try to go from, we will start, as you see, from the radioactivity. That's going to be my starting point for this journey into nuclear physics. We're going to start by the main protagonist into radioactivity and see how this field has evolved into nuclear physics. And as I said, there will be a mix between historical fact, anecdotes that hopefully make the talk a bit more lively, interesting, and then some physical concepts. So, and I will be jumping between these 2 or 3 topics like that. Feel free to ask your question in the chat, in the Q&A. Hopefully I will see them. If I don't see them because I'm focusing on the talk, maybe the other panelists can mention that there's a question to be answered. And then at the end of the talk, I will stop, and then there will be hopefully some discussion. So we'll keep it about, like, maybe I will talk about 40 minutes and then 40, 50, and then we have like a 10 minutes discussion, something like that. So let me first start by sharing the screen, so then we can start this. And then if I this in full screen, so you should be able to see my screen, full screen, and also my pointer. So if I underline something, then you could see that, right? All right. So in particle physics, what we do, I mean, what the community is doing is basically colliding particles. It can be protons, can be isotope or electrons or other particles. We collide them with enough energy to hopefully break them into their constituent, and then from the decay product that are measured, trying to reconstruct the interaction, trying to build an understanding of what really happened at the center of the collision based on the debris. So this is like a sketch from Raoul introduction last year. So you have a collision that happened in the center of a detector, and then the particles reach the detector here, and then there's some electronic devices that record some signal, and then eventually goes to your screen, right? So question that arise when you look at the historical perspective, how this field started. I mean, how do we make beams? What was the first beam that started all this? And then, as I said, we're going to start by talking about radioactivity. So starting point that I choose that things a bit more natural. So we'll see different protagonists. And then the first 3 here that are mentioned is the Pierre and Marie Curie, the famous couple, and also Becquerel. So this lady and gentleman, they were studying natural phenomena such as fluorescence. So fluorescence is the natural emission of a material, and natural emission of light, right? So they were studying properties of material that were emitting something, light, or as we're going to see, some other things. There were other protagonism at the same time. Rutherford, for instance, we're going to talk about a lot about Rutherford here, and also Villard, another French person, right? So the one also I want to mention that here I illustrate that what we know from radioactivity. So you can see some picture here that represent the current knowledge. That those blue and red dot correspond to proton and neutron that we know now that form the nucleus. So this is a nucleus, and those some isotope of some nucleus are unstable. They produce some particle. So what I'm saying that one needs to be careful is that, of course, back in the day, so when you look at 125 years ago, 130 years ago, of course, people did not have this understanding. This picture is not what those people had in mind, right? For them, their reality was a substance that was emitting either light or other things. And how did they know that? Is because when they would place that substance within some other detector, like some photovoltaic things, they would note a signal. So they were guessing that the substance they placed emits something invisible for our eyes, and they had to understanding what kind of process it was. So again, so be careful about all the picture I'm drawing. They reflect typically our understanding nowadays, but not what they were knowing, right? So the first thing is, as you know now, there's like three main types of radioactivity. We call them alpha, beta, and gamma. And now we know that alpha particle, alpha decays correspond to the emission of two protons and two neutrons, like a nucleus of helium. The beta decay is the emission of an electron, and the gamma decay of X-rays, light, energetic light. Now, how these ladies and gentlemen discovered these three types of radioactivity is Rutherford. So Rutherford was knew that everybody was working on similar things. He is the first one who took different materials and then placed a sheet of paper, a simple sheet of paper between the material and the detector. And notice that some material, well, their emission was absorbed by this sheet of paper, and from other not. So he said, well, if the sheet of paper just absorb all the radioactivity, what was called later the radioactivity, then I'm calling that alpha radioactivity. And then if it goes through, I call that beta, and then gamma. There were other ways of distinguish between beta and gamma. But Rutherford was really the first to come with these ideas of separation by absorption from a single sheet of paper. So he came up with the name. And then they also quickly realized that the emission of these particles, so alpha and beta, they were electrically charged. So how do you know that a particle is has an electric charge? You place them into a magnetic field and you look for deviations. If you place an electric charge into a magnetic field, it describes a circle to the left or to the right, depending on the charge. So that's how they could see that alpha particle was positively charged, where this beta was negatively charged. So with this knowledge of having alpha particle, so as I said, they called that alpha particle. They had no idea what it was, but they knew that it was positively charged and it was fairly heavy. The detection of mass is fairly straightforward because it's related to the energy that particle deposits into the detector. The electron was actually discovered by Thomson just recently. So the electron was discovered a couple of years before, in the same decade as radioactivity was discovered by the protagonist we mentioned, and by Thomson. And Thomson had a model for the atom. His idea was that because he knew that there were electrons, they were negatively charged, so well, maybe my atom is just what they call a pudding, a plum pudding with some positively charged particle diffused into the atom and some punctual grain of electron, right? So that was his model. So Rutherford just barely discovered this alpha particle and said, well, this can actually be used to make a beam. You know, if I put my source of alpha particle, maybe I can shoot them to other atoms and see if that Thomson model is correct. So in that case, you would expect that if you shoot alpha particle to some, let's say, a gold foil, that's what he did. Well, we'll see that it's not exactly him, but his colleague did. Then if Thomson model is correct, then we should expect very minor deviation from this. Reason is the positive charge would repel the positive charge of the atom, but this positive charge is diffused inside the nucleus. So the diffusion will make like the deviation very small. So that's why you expect small deviation. Rutherford's idea was like, well, yes, but maybe it's not the case. It's like he was anticipating. It was like, maybe it's not the case. So instead of trying to detect all the particles just directly in front of the beam, maybe we should put detector everywhere, because maybe this will happen. He didn't know. He said, well, but we have to think about that possibility, that maybe my beam of alpha particles is not going to go straight, but it's going to bounce back. That was probably a crazy idea at that time, say unconventional idea, but his idea was to place detector all around just to see in case it happens. And then we're going to see that it did happen like that. And then the interpretation he found was like, oh, okay, so if it bounced back, it's maybe because the positive charge is actually not diffused through all the atom, but very localized into the center of the atom, which we are called the nucleus, the nucleus of the atom, right? So we see that he had like, it's very important to see the philosophy that we had a model, like the Thomson model, and then we want to test that. So we make an experiment, and then the experiment goes quote unquote wrong, in the sense that there is a discrepancy between the theory prediction and then the experiment. Now, Rutherford's resolution of that was to actually change completely the model of the atom and then invent the nucleus. So this anecdote, let me generalize that a little bit more on a philosophical ground. So typically when there is a contradiction between a theory and an experiment, there are like three different outcomes, three different possibility to resolve this conflict. Well, the first is very trivial, is that there is a mistake, either in the theory or the experiment. I mean, this may happen, but this is not the interesting resolution. There are two different resolutions. The one with for instance, the invention of a new concept, the nucleus. We call that the ontological solution. Ontological means creation of something, the fact that something exists. So in the case of Rutherford, it was the invention, the introduction of a new concept called the nucleus, right? Another example in particle physics that you may have heard about is the discovery of the neutrino. So the neutrino comes from, you take some neutron and then you let this neutron decay. The neutron has a fixed mass. We know the mass of the neutron. If it decays only to a proton and an electron, so the neutrino will be this new particle. So let's pretend it's not there. Let's pretend that our understanding is that a neutron decays into a proton and an electron. Why I'm saying that? Because this is what we see. The proton has a positive charge, and the electron has a negative charge. So if we could have like a bag of neutron, let's say, and leave it there, then along the time we would see proton and electron popping up by pair in two different opposite directions. and we can measure the energy. And if the neutron has a fixed mass, decay into two particles, where also their mass are fixed, we know the mass of the proton and the electron, then it's not difficult to see that the speed of this particle need to be fixed. Like typically the energy, when I say speed, can be the kinetic energy. The energy is fixed. So if the neutron decays into a proton and a neutron, what we call the spectrum of the electron, that means the number of electrons of a given energy, should be very specific. Should be only one energy allowed, right? So people did actually that. They say, okay, let's take neutron, let's wait them for them to decay, and then looks at the spectrum of the electron. And then they found this. They found the green line. They didn't find like only a single energy. They found the whole spectrum. And the resolution of this was by Wolfgang Pauli, who was Italian, and then say, well, maybe there's a little neutral guy, which would translate into in Italian to neutrino. Ino means little, if you wish, in Italian. So of course, nobody could detect the neutrino at that time, but it was a resolution of this conflict. So this is another example of what we call an ontological solution to a conflict between theory and experiment that lead to the existence or discovery or invention, if you want, of new concept, of new particle. There's an alternative solution, which called that the legislative. Legislative means you change the law. Another example, very famous, is that you take Newton's law, you compute when the Mercury is passing to its closest position to the sun, and then you compute when actually this position changes over time. Right? This is called a precession. So the point where on the orbit where Mercury is closest to the sun actually changes over time. So this ellipse here moves around time. So this point here moves. And Newton's law gives you a prediction for that. And that prediction was in clear disagreement with experiment as soon as we could measure that. The resolution of this problem, of this conflict, was actually to replace Newton's law by another more general law, general relativity. The general relativity actually reduces to Newton's law into some limit, small masses, small speed, etc. So this is another example of a different procedure to resolve a conflict called a legislative. You change the law, right? All right, so that was a parenthesis about how to, a philosophical digression about resolution of contradiction between theory and experiment, right? All right, so let's come back to our experiment. So as I said, it's not exactly Rutherford who did that. Rutherford was running a lab in UK. He had the resources to design the experiment, the idea, but the experiment was actually carried by two other persons. So Geiger was already an established professor in Germany, was on sabbatical to visit Rutherford's lab. And there were like a student, Marcel. So if you look at actually the date, so Marcel was not even 20 years old when he actually carried this experiment. So that's probably some of you are around this age. So you see that back in the day, so these people, they could do this. So there's no, you don't need to wait to be old to carry the important physics, I think. So what was the design of the experiment is that you take your radioactive sources, you enclose it into a very heavy box that absorbs all the emission, the radioactivity, except for one hole. And then you make a beam out of that. So all the particles can actually fly through the hole. And then in the direction of flight, then you put a golden foil, right? And around that, then you put a detector, right? And this detector, you can actually divide it by what we call a solid angle. A solid angle is just a portion of a sphere. So why we do that is because we are interested to note in which direction they come. Because maybe that would give us some information about the interaction. So just a parenthesis, what is this notation? D omega, it's what we call a solid angle. So one angle is a portion of a circle. A solid angle is just a portion of a sphere. So just an illustration, if you're not familiar with that, it's just a solid angle is like the generalization. I mean, it's just a direction. It's just a portion of your vision, portion of sphere, right? I should say that I will make the slide available probably on the Dropbox. I think you should have access to a Dropbox. I will give the slide. I will put the slide in the Dropbox, so for you to have access to that, you can review that. There will be some exercise if you wish to do that. So what do we measure actually? So in particle physics or nuclear physics, we call this what we measure. We call that a cross section or a differential cross section. Differential means respect to some direction, for instance, respect to some variable. And a cross section, why the name cross section, is because it's literally a transverse area. So section means area, it's like the area, and cross means transverse. It's the transverse area perpendicular to the beam where an interaction occurs. So the bigger this area is, the more interaction there is. So that's why we say the bigger the cross section is, then the more interaction. Okay. So the cross section has literally the dimension of an area. But of course, we don't measure experimentally. We do not measure an area. We just measure a number of particles that arrive by solid angle, right? So the way we compute a cross-section from the experimentalist point of view, and we'll see the theory point of view, is just by counting the number of particles by solid angles. So that's what we do. But you're gonna say, well, yeah, but the more people enter, the more people you shoot, then the more people you collect. That's true. So you need to renormalize by the initial flux. So this initial flux has a name. We call that luminosity. So physicist has always been, inventive with name, and then we will see that there will be like some funny names along this talk. So the luminosity is simply the number is proportional to the number of incident particles. And of course, you need to divide by the number of time and then by the area or the section of the beam. I mean, just to make everything consistent, right? And you divide by that because you want to collect the number of particles. This is proportional to the number of incident particles, right? So what are the typical order of magnitude? So it's very important for a physicist to have order of magnitude in mind, just to have an idea that your basic calculation is not totally wrong. So typically at the LHC, so the LHC is the biggest accelerator that humanity ever built. For now, it runs at CERN. It's like a 27 kilometers, a ring of 27 kilometers long. The order of magnitude is 10 to 34. This is a huge number, 10 to 34 proton per centimeter square per second. This is a huge number. Okay? Now, as I said, so this is per unit of angle. And then, of course, the cross-section is the integration, the sum over all this direction. So d omega is a direction, you sum over that. Okay, so that's how people compute. Again, if you want to have some order of magnitude, so this is taken from the particle data group, which is a website that compiles a lot of information about particle physics in general. So you can have plot about, so this is the cross-section of proton-proton scattering at different energy. So this is the energy in the center of mass, all right? And then the unit is a unit that GV, so you may be not very familiar with GV, we will come back to that. So with Einstein relation, you can convert GV to mass because E equal mc2. So if you convert kilograms to GV, then 1 proton is about 1 GV. Okay, so 1 GV is the energy that corresponds to the mass of a single proton. Okay, but then of course those protons are actually accelerated, so they have like a kinetic energy. So that's why the energy is bigger than 1, because and then you can see that the order of magnitude of the cross section is at standard energy. So at the LHC, we can reach 13 TeV. Then we have 0.1 bar. And I will come to this unit. What does that mean? The bar, which corresponds to 10 to minus 25 centimeters square. So what does that mean physically? That means that when you accelerate proton at having a kinetic energy, which is like 13,000 times their mass, you smash them together, the area of interaction of this is about 10 to 25 centimeters square, all right? Now, when you combine that with the luminosity, and then you can guess what's the order of magnitude of collision per second. Combine these two numbers, and then you see that you have 10 to 9. So you have a billion collision per second. So this number is very important because when you design the detector and the machinery, you need to make sure that you can handle 10 to a billion of collision per second. You need to treat that live. You know, you have like a lot of information that comes from every collision. Right. So this is one, for instance, dealing with all this data coming was one of the major challenge also from CERN. So they created a grid across mostly France, where actually the data are shared and treated separately in parallel, etc., etc. All right. So I talk about barns and electron volt. Electron volt, in terms of unit, is the energy acquired by an electron accelerated by a potential of 1 volt. All right. So this is just to keep order of magnitude of the order of 1 or 1,000 in particle physics, because you see that if you were to keep the joule, then you see that you have a factor of 10 to minus 19. Okay, but in particle physics, typically we have MeV, GeV, maybe TeV, but GeV, so a giga electron volt means a million of electron volt. So that's the order of magnitude. That's one unit that we mentioned. Another interesting unit is called the bar. Now this one is kind of funny. So the origin of the name comes back to the Manhattan Project during World War II. The US were all the physicists and most of the scientists during World War II in the US, they were all trying to build the bomb, right? Just trying to get to build the bomb faster than the German, right? So they were studying. Oh, there's a question. No, open. Okay, let me pause, and then when calculating the differential cross-section, are the particles always referred to in terms of proton, or does the type of particle change according to the experiment? So the definition of the cross-section is very general. It's the same. Here I'm taking the example of protons. You can change to alpha particles, as we're going to do. It's exactly the same. Everything here is really independent of the beam. Okay? Yes. Now, coming back to, so this has been answered. Okay, so what does sigma pp represent? Yes, good. So sigma pp is the total cross-section for 2 protons. That means that you shoot a proton to another proton at that energy in the center of mass. So what Rutherford did was shooting an alpha particle into a gold. That would be the sigma alpha gold And here the data I'm showing you that has to do with the LHC is sigma pp, proton, proton. All right. So let me see if I can, okay. All right, so if I click on that, it means that the question has been answered. All right, okay, I should be done, okay. All right, yes, so don't hesitate to ask your question. Now, the barn, interestingly, the barn comes from because they needed to invent a unit, but they didn't want to make it clear that they were studying nuclear reaction. So the term barn, I invite you to Google in Wikipedia. You're going to find, if you ask Wikipedia the barn, the unit, you're going to find the story. It's because there's a US expression saying that even a bad shooter cannot miss the side of the barn. A barn is like a big thing that you. Of course, we're talking. This expression come back from the Far West in the US, where everybody, shooting is a common practice back in the days. So they were using the barn, coming from this expression, using that because it's something big, because they were finding that the cross section of two uranium were big. And why is it big? Because the uranium itself is now we know it's a big atom. Okay, and the conversion is that one barn is 10 to minus 28 meters square or 100 femtometer. So the radius, more or less the radius of an atom is the order of 10 femtometers, of 10 to the 15 fermimeters. There's other question in the chat. Could you please explain the graph again? So this graph is the cross section here on the vertical axis, measured in millibars. So that's the area of interaction, which is proportional to the number of collision that happens, as a function of the energy. So you have two protons going head to head, and then the speed or the kinetic energy of this particle can be fine-tuned. Every point here corresponds to a single experiment. You do an experiment where the energy is 10 GeV, and then you get this point. I didn't explain the different curve. The elastic curve is when the two protons, they actually interact, but they do not break apart. You actually find two protons in the final state. If they do break apart, they call that inelastic. And total is nothing but the sum of the two. Okay? So that's the free curve. So most of these data points come from labs, from that we done, except the green points that come from cosmic points. Cosmic points is when we study the cosmic rays, and we come to that. Cosmic rays has been important to discover new particles. So typically, there are protons that are produced in nuclear reaction in stars, and they fly freely through space. Nothing stops them. Space is mostly empty, except at some point they come to Earth. And the Earth is not empty. We have clouds. We have an atmosphere. So the proton come into the atmosphere. The atmosphere is mainly hydrogen or the particle, but it's mainly proton, let's say roughly. So it's also proton-proton interaction. Okay. All right. So that's us. Okay. Could you please say why center of mass frame is relevant? So this is really the energy. When you specify quantities, you need to know in which frame you are. So I'm sitting in, I see them head to head. Of course, if I'm sitting on the top of a proton, well, its energy, if I'm at rest respect to the proton, its energy, its kinetic energy is zero, is at rest. Okay. And then I see the other one having like a bigger kinetic energy. So we need to find a frame just to make sure that we talk about the same thing. A common frame is the center of mass frame, where the two particles are coming head to head. Okay. All right. So that was okay. What do elastic? Oh, I think I explained that. Okay. So great. All right. Very good. Okay, so that was for the bar. Yes, and then I will also explain that if you take Einstein relation, then a proton mass is roughly 1 JeV, a million of MeV. All right, very good. So we saw how, and then yes, so in the, I have to keep the time. Okay, well, maybe 10 more minutes. So when I explained how to compute the cross-section for the experimental point of view. We collect data in different angular direction. Okay, but how, if we have a model for the interaction, how do we compute actually a cross-section? So then we have to look at the theory point of view. So this is the area where an interaction happened. So we have our beam, this is the blue, and here in this, I'm not gonna do a head-to-head collision. I'm gonna consider like the target is at rest. So here, this is a frame where the target is at rest and I'm shooting. Like, so this is my alpha particle, and then this is my gold foil. Yeah, and my gold foil here, for instance, is going to be like some sphere, it's going to interact with some to some hard sphere that we'll do the calculation later on. So if there is a deviation, that means that we have a particle that's coming and then it deviates, so we see it at a different angle. So something happened, an interaction happened. So what's the interaction, the transverse area where this interaction happened? Well, this is actually this this disk here. This is a disk. This is a transverse disk. So imagine that if I shoot outside this disk, I miss the sphere and then I fly by, and I don't have an interaction, and I don't record that as an event. Okay. So to have an interaction, I have to be within that circle. But what matters is that, of course, if I shoot here, I deviate in that direction. If I shoot maybe here, I deviate in another direction, okay? So we need to have the relation where the relation between the impact factor here, the distance to the radius, to the head-to-head collision, and the angle where it arrives in the detector. So to do that, there's a little bit of math. We have to compute this elemental. So a D always means infinitesimally small, right? Very, very, very small. So the area, the infinitely small transverse area, because always in mathematics and physics, we look at the limit where everything is small, we're going to have derivative, integral, etc. Because if I consider something very small, I can approximate that everything is constant, that everything happens here, arrive here. So if B is my offset, then the area here is proportional to dB, the increment. So this is B, this is dB. There's a line B, there's a line dB. And then the other dimension here, this other dimension here, is a portion of a circle. So if the angle is d theta, theta is the angle here, then the length of this is the radius times the angle. So the radius is B. So this is a radius B, this is a radius dB. So the difference between the two is dB, because this is B plus dB, this is B. And then the length of this is just the radius times the angle, so B dB. So let me see, there's another question here. What are the primary methods used to detect and measure radiation in nuclear physics experiment, and how do they work? All right, so I'm not super qualified to answer this question. I'm guessing they have some equipment that, measure, like if you have like some wires that when you have a charged particles that come very close to the wires, then this induces a current that you measure. That's one of the technique. There are other techniques. So this, I would just leave that to my experimental colleagues. So maybe other people who can answer that. But so there are plenty of techniques, but I'm not an expert of that. So now, so So okay, so this is d sigma in terms of the impact factor, and then the angle, the scattering angle here, the portion when it happens can be also decomposed into the two angles phi and theta that actually refer to the direction. Okay, so the cross section has like this expression that here looks like and very difficult to understand. What does that mean? But typically, if you have a model of in which angle the particle arrive when it's shoot from an offset, an impact factor of b, if you have a model for that, then you can compute the cross section. We're going to do an exercise to make sure that this is clear. So typically, a very easy exercise, and we're going to do that, and I will invite you to redo it. What's the difference between nuclear physics and particle physics? Very good question. Because the border is very gray. All right. So typically would be that the difference would be the scale of energy. Nuclear has to do with nucleus, and typically these particles are heavier. So we're talking about protons from uranium. Uranium is very massive, right? The nuclear physics, their topic is more like related to everything with isotopes or nuclear material, where actually the interaction of the nucleons within this isotope, within this nuclei, are the relative speed of the protons are fairly small. So we can do what we call some non-relativistic approximation, meaning that nuclear physics is a little bit closer to classical physics, where particle physics is the opposite end of the spectrum, is typically where energy are higher, and you cannot do this non-relativistic approximation. And then in between, then you have like the Jeff scale. So from nuclear, you go from the keV, 1,000 electron volt, to Jeff, then you have the Jeff area, and then when you go to the TeV, tera electron volt, and then you go to particle physics. So typically particle physics is more like a very high energy scattering experiment when you have other type of particles that are involved. Of course, you can mix the two. I have colleagues that work in nuclear physics trying to find some new particles. So the combined technique of both. So there's a gray area between physics and particle physics. It's also come from the background. If you have a more background on non-relativistic physics or ultra-relativistic physics. While doing all this experiment and treating entities as particles, how do we handle the wave nature of this entity and uncertainty moment? So there's a whole formalism for that. So this is what you learn at school. I'm not gonna tell you how to do that in this talks. There are techniques. So you start from, so typically the non-relativistic approach comes from quantum mechanics. Quantum mechanics is typically non-relativistic. Quantum mechanics include the wave nature of the particles, all right? And there's a whole formalism. Then if you include relativistic effect, so that means taking into account length, contraction, dilatation of time, things like that, then you move to particle physics or nuclear physics, right? So there's a whole formalism. As I said, at the university first you learn quantum mechanics, and then you move to include some relativistic effects along the way to move to particle physics. All right. So if I sketch this derivation, and I invite you to redo it step by step, we shoot a projectile, a point-like projectile, into a hard sphere with a radius r. So this hard sphere is extremely heavy, so no recoil, it's not going to move, and then the bounce is going to be purely elastic. So this is actually a classical calculation. So everything is like, this is billiards. Billiard with a very small ball on a very heavy ball, okay? the outgoing speed is actually the same as the ingoing speed, and the angle of refraction is the same. So these two quantity, they comes from two conservation of energy and of angular momentum that you may have heard about that. All right. So what do we do from that? Then we need an expression for, we need, there's another question. Can we increase the cross-section area and what are the advantages? So you cannot increase, well, so you measure that. So if we come back, so those are actually measurement, okay? So there is a nature, tell what's the cross-section between two protons at that energy. It's not that the human cannot decide that the interaction of two protons at that energy is going to be much bigger or much smaller. No, this is fixed by nature. We actually trying to understand if we can explain that numbers from an interaction, but we cannot fine-tune that, right? If this is, that's right. So now if we come back to the exercise, so we have to do some basic manipulation. We want to have B, the impact factor, as a function of theta, just to make this derivation here. So that means that for a given B, we have to know what's the angle theta of outgoing. So this is some geometry, and you can do that, and then you have a relation. So R is fixed, and then you have this. So I can derive, and then I can this. So here there is an absolute value, because of course this is a positive number. So I have to get rid of sign here. And then you see that the sine theta half can be, there was some sound. Okay, I don't know. It's, anyway, so when you actually simplify this expression, so you replace B by here and then here, you find that the differential cross-section is actually a constant. According to, that means that if you actually shoot from the same B, the number you shoot from different Bs everywhere, the number of particles in every direction is going to be the same. And now if I want to have the total cross-section, that means I sum over all the direction, then I get pi r squared. And this should ring a bell. This is what? This is actually the transverse area of a sphere. That means that the cross-section, and I say cross-section is a transverse area, the cross-section of, in classical mechanics, in billiards, if I shoot a point-like projectile according to a sphere, the cross-section, the transverse area of interaction correspond to the disk, what I see from the sphere. When I see a sphere in front of me, I actually see a disk of area pi r squared. So this makes sense, right? So this all makes sense. What does the cross-section increase with energy? Can it be into? All right. So this is actually a very complicated problem. So here you can see that the cross-section increase with energy. You can actually show from conservation of probability that this is actually allowed by in quantum field theory, not classically not, but with quantum field theory, by conservation of probability, the area can actually grow as fast as some logarithm of the energy, logarithm square, actually. That's the maximum bound. And the reason for that, it's not easy to explain. It's related to a particle that, well, something that can be exchanged called the Pomeron. I'm not going to enter into the details. It's very complicated. But the rise of a cross section can be explained. Well, it can be allowed by just conservation of probability. That means that whatever enters needs to go out, and some relativistic effect. So what I'm arriving the end of this first section, and then yes, we're gonna. So I had another couple of things to say, maybe 1 or 2 minutes, because we have a hard deadline at 6. Well, Yeah? So the thing is that when Rutherford did the experiment, he actually found that there were like there were like 1 every 20,000 alpha particle who were bouncing back a very large angle. So this is a very small number, 1 over 20,000, but this is not zero, and that was realistically possible to see. What I mean by that is what we were more or less lucky that this 20,000 was not 20 million, because if the so this is of course proportional to the size of the nucleus, right? So you imagine that if the nucleus was even smaller, and that number 20,000 would be 20 million, 20 billion, I don't know, then maybe Rutherford would not have seen anything, right? It would, but we were fortunate enough, well, he was fortunate enough that given the setup, the beam time, everything, then he could actually spot a couple of deviation, even though that he was 1 every 20,000 particle. And then because of that, he could actually find the size of the nucleon. So this requires a little bit more of calculation. So he said, okay, this is not exactly a hard sphere. So the scattering between a point like alpha particle into a hard sphere nucleus, we done the calculation. But he knew that it was a little bit more complicated than that. He said, no, the interaction must be from Coulomb force, electric repulsion between the electric charge of the alpha particle and the nucleus. So he did that calculation, it's much more complicated than the one we did, and then he found this law, right? This law can be found in textbooks. You maybe see that later. And then he compared that to experiment, and he saw a very nice agreement. You see that here when we were doing the hard sphere, there were no theta dependence. It was isotropic. Here we do have a angular dependence, but moreover we have an energy dependence here. 1 over E squared. E is the energy. This is here energy. So you see this is 1 over E squared. This is like 1 over x squared, if you want, this line, right? And then you see a very nice agreement, and I will finish by that. But you see a nice agreement, but you see also deviation after a certain energy. So he actually thought about that. They say, well, it's actually nice because when there is an agreement, is because the energy, the particle arrives and then feels the Coulomb force. But then after a certain energy, the particle energy is too big and actually get too close and then actually penetrates the nucleus. So if the particle penetrates the nucleus, it's not a Coulomb force, it's something else, it's more complicated. And my formula doesn't work. And so he says, once there is this transition between Coulomb and non-Coulomb, this is when this energy corresponds to the energy to penetrate the barrier factor, the Coulomb, and penetrate to the nucleus itself. With this number here, he was able actually to guess what was the radius of that. And when you plug number together, we found that this is actually 10 to a femtometers. That was what we were saying, that, we were saying that 1 barn corresponds to this square. And then indeed, so the typical radius of a nucleon computed by Rutherford is the order of a femtometers, right? With that. And I think I will stop there because then we have to. I will pause the slide and then there will be some exercise here and there. But unfortunately, we have a hard cutoff. So I see there are 3 more comments. I'm going to print them because there is like some textbook recommendation. Should we prepare a report to submit for this week? Yes, I think you have received instruction. I will check with Raoul to see. Let me first unshare my screen because I think we have probably more people coming. So I will I don't know if the Slack is already set up because it's the first week. So this I will have to check. I'm sorry because so a textbook, okay. The probably were, how do we know the error sensitive to the false reading? I cannot answer that question. We don't know. So this is very technical and I'm not qualified to answer that. So I'm sorry about that. Nuclear, when a particle speed is comparable to the speed of light, can we use the same mathematical? No, exactly. So there is the non-relativistic formalism and there is the relativistic one. So that's the main difference. If particles are slow compared to the speed of light, then we can use non-relativistic approximation. If they are not, then we cannot. Right? That answers the question. Okay, done. Any textbook? So this textbook, I will try to find some and then mention that in the Slack or by email. I'll do that. Okay. No, sir, it isn't. Okay. Okay. So I guess it was the. So so for the report, I will communicate. Yes. So what are the main difference between natural and artificial isotope? Artificial means that they are created in the lab. Natural means they are actually naturally present in the universe. And I think with that, I have to leave because there's somebody else